Alright friends, welcome back. In this video I'd like to go ahead and do a part 1. I want to kind of handle the video for today in a little bit of a different way. So there's basically 3 major topics that we need to cover in the first day here of P.5, and so I'm going to go ahead and split those up into 3 different little mini videos instead of having just like one gargantuan video. So this is the first one of those little mini videos, and this video specifically what I want to do is I want to talk about the domain of an expression, okay? Now, domain is something that you guys have learned about for a long time now in a lot of your different algebra classes, domain and range. And I think everybody is pretty comfortable with the idea that the domain represents all of the x values, right? But I feel like one of the parts of the definition that's often left out is the fact that, yes, it's all the x values, but it's all of the ones that are allowed, right? It's all of the ones that are allowed. And what I mean by that is that they don't break any of our rules of algebra. Okay, we have a lot of different rules of algebra that you guys have been learning about for a very long time, and it would be a shame if we plugged in an x and that x caused one of those rules to break. Okay, and so specifically what I want you guys to be on the lookout for are 2 special situations. Okay, I want you to look out for expressions with fractions in them, and I also want you to look out for expressions with radicals in them. Sometimes it's just going to have fractions, sometimes it's just going to have radicals, sometimes it's going to have both, okay? So these are going to be situations I want you to look out for because these are probably 2 of the most important rules of algebra that we want to try to never break, okay? The first one is dividing by 0. We all know that one, right? You can never divide by 0. And so that means if you ever have a fraction, that's something that you're dividing by, right? You have a numerator divided by a denominator, and so that means that we are going to need to avoid dividing by 0 by setting the denominator not equal to 0. What you're saying is that whatever shows up in the denominator, it is not allowed to be equal to 0. Okay? The other thing is when you have radicals. Okay? And for the most part, radicals are fine, except for when you have an even radical. There's just one thing that we need to be careful of, and that's taking an even radical of a negative number. Okay, and so even radical, what do I mean by that? Well, I mean when the index is an even number, like a square root, the index is 2, an even number. A 4th root, the index is 4, that's an even number. Same thing for a 6th root, an 8th root, a 10th root. Any type of root where the index is even, we have to be a little bit more careful because we can never take the even root of a negative number. So when you have the part underneath the square root, that's something that we call the radicand. That is something that I want you to always set to be greater than or equal to 0. Okay? So we have a couple of different things that I want you to be on the lookout for here, and depending on what you're looking at, you're going to do something specific to find those problem values. Okay? So we need to look out for some fractions or some radicals. So let's get started with that. Example 1, state the domain in interval notation. Okay? So remember, interval notation is a language that we can use to write out subsets of the real number line. You could find that in a previous video. That's the one with brackets and parentheses and that kind of thing. So as we look at these examples, what we want to do is we want to write out the complete list of all the x values that you are allowed to plug into this expression without breaking any rules, okay? So if you look at part A there, that's just a simple polynomial. It just says, what do I do with my x when I plug it in? Well, I got to take x to the power of 3 first, and then after that I have to add on whatever 3 times x is, and then after that I got to take away a 14, okay? These are all things that this expression requires you to do, and here's the thing. At no point in this expression, when you plug in an x, do you ever have to divide by anything. At no point do you ever have to take an even root, okay? And so this is something that does not have any restrictions on its domain, which means that you could plug in any number you want into this expression and not break any of your rules. So what we want to say here is that the domain is all real numbers, and since we do have to specifically use interval notation to do that, we need to remember how to represent that in interval notation. That would just be the open interval from negative infinity all the way to positive infinity. Okay, so that represents every single real number that exists. So that will be our domain for that one. Okay, so that one didn't have any problems. As we look at these other examples, we might have to notice that we do have some certain things going on, like here in part B. Okay, this is an even root. Okay, so the root on a square root, or sorry, the index on a square root, that is going to have to be a 2, and so this is going to be an even root. And so here's how I want you to take care of this. The part that shows up under the square root, that's the expression 2x minus 3. What I want you to do is separately off to the side, I want you to go ahead and say that 2x minus 3, since it's under an even root, I have to say that this is not allowed to be equal to 0. Okay? So that's what I want to see you do anytime you have an even root, is take what's under the root and set it not equal to 0. Okay? So what that's going to basically do is it's going to give you a way to figure out what x itself cannot be equal to, okay? So what we're going to do is we're going to basically solve this just like a regular equation, just doing inverse operations. Add 3 to both sides, and then that's going to give us 2x is not equal to 3, and then divide both sides by 2, and so we would see here that x is not allowed to be equal to 3 over 2, okay? So, or actually, my goodness, I am doing the wrong thing, okay? I need to say that instead this has to be greater than or equal to 0, right? I'm mixing my rules up because before, that's what you do whenever you have a denominator is you say it can't be equal to 0. That's not what I have. I have an even radical. So I'm going to say that has to be greater than or equal to 0. Sorry, guys. There we go. So not too much changes there. Still the same steps apply. But instead of saying x cannot equal to 3 over 2, it's going to be x has to be greater than or equal to 3 over 2. So keep in mind what we're saying, right? We're saying that in this original expression here with the square root and all, if you want to plug in an x, then you can do that as long as the x that you pick comes out of this list. Or in other words, the list of all of the real numbers that are greater than or equal to 3 over 2. And we do have to represent that using interval notation. So the way we would do that is a bracket with a 3 over 2 to signify that I am including that endpoint value. And then since there are infinitely many values that are greater than 3 over 2, I'm just going to go ahead and say positive infinity there, okay? And that would be the way to represent my solution set in interval notation. Doing part C here really quick, it looks like I do have a radical there, but it is a radical with an odd number root on it, or an odd number index, and that's not the special case that we need to look out for. So that is an odd index, so I'm just going to go ahead and say that I am allowed to plug in anything I want. It's only the case when you have an even index on your square root that you have to specifically do what we did in part B there, okay? If you look at part D, that does not have any radicals in it whatsoever, but it does have some denominators. Okay, matter of fact, I shouldn't say some denominators. It only has one denominator, and it's just this expression right here. And so this is what I want to see you guys doing on these examples, is saying that the denominator looks like x minus 1. Because it's a denominator, here's where we're going to say that this is not allowed to be equal to 0. Okay, and then we'll just go ahead and solve this just like a regular equation. So add 1 to both sides, and we'll see here that x is not allowed to be equal to positive 1. Okay, and so again, what we're saying here in our domain is that you could plug in any number you want into this original expression, numerator over denominator, and you're always going to get something that's good value as long as you do not plug in positive 1. Okay, and we do need to represent that using interval notation, and I oftentimes think that for sometimes when we have inequalities here, it's oftentimes easier to go ahead and write that on a number line, right? So we'll draw a number line, we'll mark our problem value there, and since that's a problem value that we cannot equal to, we're going to go ahead and put an open dot on that. But since we can be any other number in the existence, that means I'm going to go ahead and shade the entire rest of the number line here. Okay? And so, what does that mean? Well, I can go ahead and represent this, since this goes all the way out to negative infinity, and this goes all the way out to positive infinity. I could represent this as two separate intervals joined by a union symbol. Okay? So that first interval will be the open interval from negative infinity all the way up into my problem value, which is positive 1. And then my other interval will be the one that starts at positive 1 and goes all the way out to positive infinity. And that will be my domain written in interval notation for that example there. In part E, you just have two different denominators here, so all you would have to do is just go ahead and say them separately. So this denominator can't equal 0, the other denominator can't equal 0, okay? And then you would just want to solve these. So if you would solve this one up, this would be x cannot be equal to positive 1/2. And if you were to draw the number line for this, then mark your two problem values. There's 0, there is 1/2. What we want to do is put some open dots on 0 and 1/2, and then just literally shade everything else. Because again, the interpretation is you could plug in anything you want as long as it's not one of these two problem values. And then you can see that that splits the region of your number line into 1, 2, 3 regions separately. And so we would just want to go ahead and write down all three of those regions, right? So that first region there, that would be the region from negative infinity all the way until you reach 0. Parentheses around both because we're not including either. And then we'll unite that with the open interval from 0 to 1/2. Parentheses around those because we're not including those endpoints. Unite that with the open interval from 1/2 to positive infinity. Okay? And so that would be our domain written in interval notation for part E there. And then lastly, here in the video, part F, we have an expression that contains both a square root and a denominator. So separately, we're going to go ahead and take care of these, right? So the denominator first, we might just go ahead and say here that x minus 3 cannot be equal to 0. add 3 to both sides, and that gives us a restriction on our domain of x cannot be equal to 3. It's not allowed to be equal to 3, okay? If we move on to the radical up here, the part underneath this square root is just simply x, and we said that the radicand also has to be greater than or equal to 0. Okay, so there's really not much to solve there. It's just another restriction on x, right? So we have 2 different restrictions on what x is allowed to be. First of all, x has to be something that's greater than or equal to 0. And secondly, x cannot be equal to 3. Okay, so if I draw my number line here, mark my problem values, right? So that would be 0 and 3 specifically. I cannot be equal to 3, so I'm going to have an open dot on 3. I can be equal to 0 because of the or equal to 0 there in my greater than or equal to. So I'm going to put a solid dot on 0, and then I would just want to go ahead and shade everything that is greater than 0, or in other words, to the right of 0. And that would be a graph that looks like that, okay? So what we would want to do is go ahead and write this using our interval notation. So that would be the interval from 0 to positive 3, including 0, but not including 3. And then we will unite that interval with the open interval from 3 all the way out to positive infinity, since there are infinitely many numbers on the left side, or sorry, the right side of positive 3 there. So that's all I want to do in this little mini video here, is just discuss domains. You have 2 other little mini videos here in your Schoology page. One of them is going to talk about simplifying rational expressions, and the other is going to talk about how to multiply and divide them. So I hope this video has been of some help to you. Let me know if you have any questions, and I'll speak to you in the next one.